I'm Ridmi Hesara and welcome back to my channel. Today we are diving into interesting algorithm in graph theory called Fleury's algorithm. It helps us find an Eulerian path or circuit in a graph by carefully choosing which edge to follow. If you are preparing for coding interviews or just love graph puzzles, you will enjoy this one. Let's jump in. Let's begin by understanding the concept of an Eulerian path and Eulerian circuit with a visual example. On the left, we have a graph showing an Eulerian path. Here, the odd degree vertices are C and D. So the path must start at one and end at the other. One valid traversal is C, D, A, B, D. On the right, we have an Eulerian circuit. All vertices have even degree. So, we can start anywhere and return to the same vertex. For example, A, B, D, C, A. This difference between a path and a circuit is the foundation of Fleury's algorithm. Here is a quick comparison to make things clearly. An Eulerian path visits every edge exactly once but starts and ends at different vertices. It exists if exactly two vertices have an odd degree. Think of it like tracing every road in a city without preparing but starting and ending at different locations. An Eulerian circuit, on the other hand, is a special Eulerian path that starts and ends at the same vertex. It exists if all vertices have an even degree. A good example is a postal route that starts and ends at the same post office while covering every street exactly once. So, we can say a graph has an Eulerian path or circuit. For an Eulerian circuit, all the vertices must have even degrees, even number of edges connected to them. For an Eulerian path, there must be exactly two vertices with odd degree. These will be the start and end of the path. Also, the graph must be connected, meaning every vertex with at least one edge must be reachable from any other such vertex. Fleury's algorithm is a step by step method to find an Eulerian path or circuit in a graph. It works by selecting edges carefully, avoiding bridges whenever possible. A bridge is an edge that, if removed, would disconnect part of the graph. Fleury's algorithm only takes a bridge when there is no other choice. This way, the graph stays connected until the very end. These are the steps of Fleury's algorithm. To apply Fleury's algorithm, first verify if the graph has an Eulerian path or circuit. Choose a starting vertex. Traverse the graph. At each step, pick an edge that is not a bridge unless there is no alternative. Print and remove the edge. Move to the connected vertex. Keep going until you cover every edge. The algorithm ensures we visit each edge exactly once and keep the graph connected as long as possible. Let's look applications of Eulerian paths. Eulerian paths are not just a theoretical concept. They solve real-world problems where every connection or route needs to be covered exactly once. For example, routine problems. Think of postal delivery or garbage collection routes. The goal is to cover every street once without unnecessary repetition. Network design. In cable or wiring layouts, Eulerian paths help avoid redundant connections and optimize resource usage. DNA sequencing. In bioinformatics, Eulerian paths are used to assemble genome fragments into complete sequences. Puzzle solving. Classic puzzles like drawing shapes without lifting your pen or retracting any edge are based on Eulerian path logic. Logistic and supply chain. It helps in planning efficient transportation paths, ensuring every required link is covered once. These applications highlight the power of Eulerian paths in solving complex yet practical challenges. Now, let's go through the Java implementation of Fleury's algorithm step by step. We start by creating a class called Fleury. Here, we represent the number of vertices in the graph. ADJ is an array of linked lists where each linked list holds the adjacency list for a vertex. This means every vertex stores the list of vertices connected to it. In the constructor, we initialize the graph with v vertices and assign an empty adjacency list for each vertex. Adding and removing edges. The method addEdge and the removeEdge allow us to add or remove an edge between two vertices u and v. Because this is an undirected graph, we add the edge in both adjacency list adju and adjv. Print Euler path. This is a core method. Starting from vertex u, it checks all connected vertices v. It uses is valid next edge to verify whether an edge can be satisfied taken. Once the edge is valid, it prints the edge, removes it and recursively calls print Euler path to continue the traversal. In this function, it ensures that we don't pick a bridge unless we have no other choice. If the current vertex u has only one edge, we can use it. Otherwise, we check by removing the edge and counting the reachable vertices using DFS. If removing the edge reduces connectivity, it means the edge is a bridge and we avoid it unless it's the last option. In this method, DFS count, this is a simple depth-first search helper method. It counts the number of vertices reachable from U. This count helps determine whether an edge is a bridge. In the main method, We create a graph with 5 vertices and it at edges 0, 1, 1, 2, 2, 0, 0, 3 and 3, 4. Finally, we print the Eulerian path by calling print Euler path starting from vertex 0. The output will print the edges in the order they are traversed. For example, Eulerian path 0, 1, 1, 2, 2, 0, 0, 3 and 3, 4. This confirms that every edge is visited exactly once, forming a valid Eulerian path. Now let's work through an example. Start from vertex 0. We visit edge 0, 1, then 1, 2, 2, 0, forming a cycle, then go from 0 to 3 and 3 to 4. Each edge is visited exactly once and the graph remains connected. That's how Fleury's algorithm carefully constructs the path. Here key takeaways. Quick recap. An Eulerian path visits every edge once. Eulerian circuit ends where it starts. Always check degree conditions and connectivity. Fleury's algorithm helps avoid bridges and ensures valid traversal. It's an elegant way to walk through a graph. To summarize, we learn the difference between Eulerian paths and circuits, understood the conditions for their existence, and explored Fleury's algorithm in detail. We saw its real world applications, worked through an example graph, and implemented it in Java. With this, you now have the knowledge and tools to solve Eulerian path problems efficiently. So, thanks for watching. If this video helped you, give it a thumbs up and subscribe for more DSA tutorials. Until then, stay curious and keep coding. Bye bye.